Okay, good to go. So today we're gonna be, again, we continue talking about creating the process, right? And then we will hopefully start the lecture on the context switch. Okay, so remember what was, let me just quickly unwind a little bit. So what we were doing last time is we were looking, essentially, we're trying to understand how exec works, right? And so the way it works is that at a high level, you create a new address space, right? Because each process has its own address space, meaning it has its own page table, right? And at a high level, again, what is going on is that we use two functions. One is called allocuvm, which allocates pages for the user part of the address space, right? So essentially, those pages will be allocated here. And the second function is called load-uvm, right? So this function will load the pages which are already allocated from disk into memory, right? At a high level, the story seems relatively simple, right? Because you say, look, doesn't seem too hard. Like, we know how to allocate pages because we already looked at allocation of kernel memory, and at the same time we know how to load stuff from files, right? But what we were doing again last time is we were looking at the implementation of those functions, and specifically we started looking at the first we were looking at allocuvm. And we said, okay, we understand this. So we just allocate a page for the page table directory. We set it to 0. Then we use this map pages function, which essentially is, remember, map pages was the function which we used for mapping the entire physical memory into kernel address space, right? Right after the boot, after booting into the kernel, right? So it was a lecture on a kernel page table. And what we're doing here, we do this in a loop. So essentially, we go page by page and map each page into memory, and we allocate pages as we go, right? So essentially, allocuvm says takes the page table directory, takes the old size of the address space, and extends it to the new size, right? Okay, so this is reasonably easy again. So map pages, we recall what map pages is. So at the core of my map pages is this function which walks page table directory, returns a page table entry, and after that our job is trivial. We'll just simply update this page table entry with the new physical address and permission bits, right? Okay, so again, we recalled all this. The second function, and this is where we stopped last time, was this load UVM. So load user virtual memory, right? And this function was a little bit more complicated. And why was that? Because we were essentially looking at what happens. Oh no, actually, load UVM was also reasonably straightforward. So essentially, we were saying so the problem actually starts even here. So if I ask you, okay, let's take a look at this function without running too fast. So essentially what we're doing here, we're loading the program in memory, right? So essentially we are, at the end of which we will be reading an inode, which we have over here. This is the inode pointer. And we'll be using a virtual address, right? And an offset within an inode and the number of bytes to essentially read something into this virtual memory, right? So essentially, if allocuvm allocated something, right? So what load UVM is doing is that it will take the actually we'll take this address at which the program has to be loaded, right? So where does this address come from? Who can tell me quickly? It's a good question. Okay, time to wake up and understand what's going on in this lecture, right? So where does this address come from? So here's my drawing of the address space. So this is a 2 GB mark. On this side, it's kernel memory. So we don't care about it right now, right? What are we loading? We're loading an ELF file from disk, right? Remember how we deal with it. What we're doing is that we had one, let me remind you here, we had one big loop, right? So essentially this is the loop. And we first read the ELF program header. We know the number of program header entries in an ELF file, right? So it's essentially, remember this table, which in the beginning of the ELF file, there will be a table, program header table, right? And each of these will point into an ELF file. And essentially the sections which are marked as loadable will have to go in memory of the program, right? Essentially, this is what we're doing here. So one of the sections may be text, one might be data, right? And remember in a homework, we were saying that sections which have a smaller size on disk than in memory, we will, like sections like BSS, we'll just load them and expand them with zeros here, right? Agree with this? So, and this is specifically what we're doing in this loop for every section, essentially in the ELF file, right? Because we have a program header table, right? For every section, we call this alloc UVM function, which allocates this memory. And then we're using the load UVM function, which essentially loads this from disk, right? So look, the load UVM is invoked with this argument. So this is the virtual address of the section in memory. So essentially, when you read the ELF file, right, this section will have a virtual address at which it has to be loaded, right? And essentially, we take it from the program header, and we also have the size of this section, right? Because we have a size of the section in the program header, and we have an offset within the inode, which within the file, right? So this error, which I was asking just a second ago, comes from the program header, the virtual address of the section, which is compiled and linked by the linker, right? Agree with this? Okay, good. So now we understand that what we're doing. The question is following, and this is where the problem is coming from. We know that this is the virtual address, right, of the program in memory. Why do we have to walk the page table here to get a page table entry? Look what we're doing with this page table entry later. We take this page table entry, right? Get it physical address. We take the physical address. And then we use this macro, which is physical to virtual conversion, converting this virtual address in yet another virtual address. Why do you think this virtual address is not equal to this one? Or maybe they are equal, but obviously if they are equal, the kernel wouldn't be doing this. You can tell me. Because we could link the executable to run at a certain virtual address. Well, this is the certain virtual address. This is where the executable is linked to run it. It comes from the ELF file. It's inside the ELF file. Remember, there will be program header table. This is coming from the program header virtual address entry, right? So this is literally the address. To be honest, it's address 0 in x86 because the programs are linked to run at address 0. Nevertheless, instead of just simply reading into the address 0, we are reading into some other address, or at least it looks like we are reading in some other virtual address. Why do we have to go this route?
I'm just guessing over here. I think, is it because the kernel is this is mapped to the lower end of the kernel, and we are changing the virtual address map again somewhere?
Not quite. Maybe I misunderstood you, but I don't think you're on the right track. Any other ideas? This is kind of important. That's why I'm stopping here, emphasizing, and I will explain what's going on, but I wanted you to guess, guys. Remember what's going on. It's one program, one process invoking exec. Exec goes into the kernel, and we're creating a new page table, a new address space, and we're loading into this new address space. The question is like, which page table is currently active? Which one has the address 0 translated by the hardware? Okay, let me stop here for a second. Let me just find an empty slide. So here, look, remember, this is important. That's why we're stopping here. Just to emphasize what's going on. Yeah, exactly, Eric. So it's because we don't want to use the virtual address from old page table in the new page table created by the exec. Exactly. But I want everyone to understand. So good job, Eric. So look, so this is the address space of a process which called exec. It has both address 0, has 2 GBs, has the kernel here, right? So this guy from somewhere here dropped into the kernel with an exec system call, right? And right now we're still running on a page table. The hardware itself is still using the page table, which essentially maps this address 0 into some physical memory, right? So if this is a physical memory, it kind of looks like 0 is mapped to 0, but don't take it. It can be anywhere, right? Most likely it's actually not 0 because we don't even use any memory below the first megabyte, right? We're creating a new address space for which we created a new page table, right? This is the old page table, and this is the new one, right? If exec will work correctly, we will eventually switch control register 3 to point to this new page table. But the hardware has not yet switched. We didn't switch it yet, right? We still, CR3 still points to the old page table. So imagine this new address space, which is translated by this page table, right? By this new page table. It also has an address 0. Imagine we want to load something in this address 0. Where is it in our address space? Do you know how to locate it? Obviously, it's not in address 0 because address 0 is some page. And this page may be anywhere. Where is it in memory? Who can tell me? It's a little bit tricky, but it has a physical address, right? So if you say, I will take a virtual address in this new page table, virtual address new, you will receive a physical address, right, of a page which maps this virtual address. So for address 0, you have to walk this page table in software yourself to receive the physical address. You get this physical address. Imagine this is where the page is, right? So how can you now access this page? Remember how we create the kernel mapping. We map all memory up to fizstop. Imagine this is fizstop. With a 2 GB shift into every address space. For example, address 0 will be mapped exactly here. If it's address fizstop, it will be mapped, I mean, not to scale, right? But it will be 2 GBs plus fizstop, right? Agree with this? And so this physical address PA, what will be the virtual address of this physical page in our old page table? Exactly, so 2 GB plus physical address. So this virtual address is 2 GBs plus physical address. And this is exactly what we are doing with this, sorry, physical to virtual macro, right? Of a physical address. We're adding 2 gigabytes. Okay, let me stop here and again, make sure that you guys understood. This is important. So it's important to understand how those page tables evolve. It's important that every page which we're using in a system is mapped in every address space with a 2 gigabyte shift, right? So essentially every address space, if this is a physical memory, let me draw it again, and this is a fistop, sorry, right? Then in every address space with a 2 gigabyte page, with a 2 gigabyte shift, every page of this region will be mapped, right? So will be mapped from starting from 2 GBs to 2 GBs plus fistop, right? Agree with this? Which means that this page will be mapped at an address, whichever it has physical address, it will be physical address plus 2 GBs, right? Agree? That's why we, no matter if you, even if you want to access a page from another address space, what you have to do, let me change color here. What you have to do is you walk the page table of that address space. It might not be the page table which is currently used by hardware, right? If we would be on a page table which is currently used by hardware, then virtual address would be correctly converted. We could just simply write into that virtual address, right? We would land on that page, right? But since it's a different address space, we have to walk it in software, get the physical address or physical page table entry, convert the page table entry into the physical address, and then use the physical to virtual macro on this physical address to get a virtual address which we can address, right? Only kernel can do that, right? Because this virtual address which is sitting here is inside the kernel address space. So inside the user part of the address space, physical to virtual macro doesn't make sense. It just, you will add 2 gigabytes, try to access kernel memory and crash, right? Because you are not allowed to do that. But for the kernel, right, because we constructed the address space in such a manner, this trick makes sense. Okay, let me stop again for questions here. I'm pretty sure there are some. All clear? So people who were following they got this idea. Okay, this is exactly what we're doing here. So one more time. So we took the virtual address, walked the page table directory, got the page table entry. We extracted physical address from a page table entry, right? Now we're saying, okay, now I can use this physical address with a physical to virtual macro, P2V, and I can pass it to this readi function. Readi will go to disk and essentially load. It will load into this address, right? But imagine this is the virtual address here, right? It's above the 2nd gigabyte because it's in the kernel address space, kernel part of the current address space, right? But this is the physical page, which we will later map into an address space, which we're creating. So in the new address space, right? In the new address space, this page in this green address space, let me like draw it over here. This page will be mapped at address 0, right? And this address space will also have 2 GBs. And of course, like don't get surprised that the very same page will be of course mapped in this address space as well at address VA, right? Do you understand that? Because like the moment you map a page into the user part of the address space, the same page is mapped twice always, right? Because it's always mapped into the kernel part of the address space, and it's also will become mapped into the user part of the address space as well. Got this idea? What could go wrong if we didn't do this? Great question, Matt. So who can tell me what could go wrong? Why are we doing this? And actually, this is in general, it's a very great way of thinking about why we're doing something. You can say, well, like, what can go wrong? Let me explain what can go wrong here. So if we wouldn't do this, remember, if we would just simply use this virtual address in a new address space, which is in our example, it's address 0 just for the sake of it, right? The read-i function would use this virtual address new, right? And it's new, it's 0, right? And the hardware itself use the old page table for the translation, right? It will be using this page table. Read-i would load something into this address, right? It's the old address space, and we loaded it in, and we loaded with the text section of a new file, of a new executable. You can say, okay, what's wrong? Let's just stay in the same address space. Why are we building the new address space altogether? The problem is that maybe somewhere halfway through the exec function, maybe not now, but later on, we run out of memory and exec has to return an error. In order to return an error, we have to preserve the old address space, right? We have to return an error to the caller. And so if we start destroying the caller's memory with the content of the new file, then okay, there will be nowhere to return, right? Agree with this? Matt, did you understand? Okay. Okay, got it. So everyone got it? Okay, everyone who was following at least. Any other questions? Let's stop. Like I can hang out here for questions. It's just important to understand how those address spaces are organized. And up until now, I was kind of like, I was explaining this kernel address space in some declarative, I was kind of pushing it on you. I was saying like, let's map it, let's do this. But it's the first example where we say, look, we mapped it in some specific manner with a 2 GB shift. And we're using this property to make sure that we can access pages in another address space. Okay, good. Okay, then we're approaching the end of this. Let me change color back to red. End of this function. So we did the read-i, read the file into the memory, right? Now we have the text section, we have the data section of a program in memory already. For us, it's time to allocate program stack because we're getting ready to run this new binary, which we just loaded in the address space. What we want to do, however, we want to introduce this idea of a guard page. Guard page is a mechanism which allows you to catch the stack overflow, right? Meaning that x86 allocates only 4,096 bytes for the stack. Linux allocates more, but the idea of the guard page still stays there because it's totally non-trivial to catch an overflow if your stack would be located right above the data, for example. You would simply start overwriting your data section and you would crash in some very mysterious manner. It could be even worse if you would start overwriting the process text section, right? Imagine debugging it with GDB, right? Instructions are changing underneath you, and you say it doesn't look like a valid instruction stream. So what is happening, right? That's why often the text is actually mapped as read-only. It's not mapped read-only by x86 though, but by real operating systems, right? And typically people introduce some kind of a guard page. Guard page is not a bulletproof mechanism because the moment you allocate something large on a stack, imagine you allocate something like what is 8,000 bytes on a stack, right? You immediately jump to this end, right? So you jump over the guard page, and for a while you will be happily overwriting the data section until you again hit the guard pages, maybe like at the offset 8,000 plus whatever, 4,000 bytes or something like that, right? You understand this, right? That the guard page is it's a best effort service, not like a bulletproof mechanism which protects you against buffer overflows, right? Okay, so let's map this guard page. So what happens here, this is how x6 is doing this. It says we will allocate, again, the same function, allocate UVM. It's just that there will be no load now. We allocate 2 pages right above the current size of the address space. So size as z is a parameter which tracks the size of the address space. So maybe you loaded the text section, maybe it's a data section here, data. What we're doing, we round it up to the next page, right? Sorry, round it up to the next page and essentially allocate 2 pages here. One of these pages will be a stack, right? And one will be a guard. And how can we introduce an exception on a guard page? What do you think? If we want to make sure that the moment we access it, we'll see a page fault or some other fault.
Make it read only. Make it
Say
read
again?
only. Make it read only.
Make it read only. But what if you accessing the guard page in a read-only manner? Your program will still be undefined because you're accessing the data which you never initialized and stuff like that. Imagine you
or else remove the user bit on it.
Yeah, you're reading the source code. Yeah, you can remove the user bit. Here I want to emphasize one important aspect. Why do we even allocate this guard page altogether? Why not to just go into the page table, right? That's page table directory. And this is a page table entry. And for this guard page, just don't set this present bit to 1. Just clear it. It means that this page is not mapped at all. Why are we wasting an extra page? What do you think? And instead of like we allocating a page and just clearing the user bit on that page, making sure that the user cannot access it, but the page is there.
Is it because it's difficult to distinguish between page faults and kind of like stack overflows?
You can say that, but that's not the reason. Because it will go to exception and try to create a new page. Actually, x6 doesn't have an on-demand paging. So the moment you see a page fault, the kernel will kill the process if it's within the user range. If the user was running and caused the page fault.
Okay.
It's a little involved, but I wanted you to understand this as well, just for the sake of it. Because I mean, since the kernel is reasonably small, so it makes sense to understand almost like every bit. At least if I understand it, I will try to explain it to you. And I mean, maybe I'm missing something. Often I can miss or I can forget, but normally I can pick it up quickly. Okay, let me explain this. Remember when we were talking about system calls just the other day, right? Remember those functions which were checking for the validity of arguments, right? Which the user is passing to the kernel. Who can tell me what was the check? Right, we were doing like a fetch integer to fetch an integer argument, for example, from the user stack. But user can fool us and says, okay, look, by the way, like I pass you, I give you a pointer, but it's not within even my address range. Address boundary check. And remember that the check was reasonably simple. We only were checking for the SZ. So remember, we were using proc SZ, right? And we were ensuring that any pointer entirely is contained within this address range, right? But what if the user passes us a pointer which is inside the guard page, right? What can happen then? If this page is not present in a page table, then what? Then a user fools out. It passes the check because this memory is smaller than the proc size. The kernel tries to access this and faults with a page fault. One possible way here is to essentially implement a smart page fault handler, which would reason about the position of a guard page within the process address space. But x6 doesn't even keep the position of the guard page. It could, like you can add the additional field to the proc data structure to make sure that, okay, that's actually an excellent homework too. And I'll think of adding it, right? Or an excellent final exam question, right? To say, what changes need to be done to make sure that we don't waste this page? It's actually a very good question. So in like, and you can reason about like inside the process, you can say, look, this is where the guard page. And if you say that the page fault is within the guard, then user is trying to fool us. So let's kill the user, right? But x86 goes a simpler route. So they instead say, okay, the kernel will always be able to access this guard page. Like, even if the user tries to fool us and passes an address at like a buffer, for example, inside the guard page, the kernel will happily use it and will write the data there. It simplifies the code a little bit, but at a cost of an additional page. If you're really like coding a production quality system, no one will let you waste the whole page for this, right? You will have to implement your logic, right? But for this educational system, it's just fine, right? So did you get this point about the clear user flag versus a more clever page fault, and why we're wasting a page? Good. I hope. Right? Okay, so this is just the tiny details of kernel development, right? It gets a little bit complicated, but again, like the beauty of it, if you read one kernel, you can read them all, kind of, right? So with a little bit of effort. That's why I'm spending so much time on the source code, making sure that we go through every function. So you have this in your head when you either program your own kernel or read another kernel, source code of Linux or BSD kernel, for example, or even Windows if you happen to work for Windows or Mac OS, right? Okay, so we allocated the program stack, all right? So we allocated the guard page, so far so good. Now we say, let's push the program arguments on a stack. Who can tell me what these program arguments are? How do we push arguments to the main function? Who remembers? Remember when we execute exec, like when your shell runs something like wc minus l, you have to pass this minus l. So how do we pass it? Who remembers?
argc argv.
Exactly. So this is this argc and argv, right? Here's an example. So normally the main function takes two arguments, argc and argv. So what is argv? Argv is an array, right? So for example, in this example, argv will contain 3 entries. So entry 0 will be the string which has the name of the program itself. Entry 1 will be the string. Here we pass 2 arguments, which contain the pointer to the string. Okay, this is the pointer to the string program. This is the pointer to the string hello. And this third one is a pointer, the third one, but number 2 is the pointer to world, right? And they could have ended with it with a 0 argument, but maybe 0 is a pointer at location 0, right? That's why it's not a very good design choice to do that, right? That's why they said, look, argc will be a size of this array. So in this example, this is 3, right? Okay, so you say, look, if I exec a program, I need a way to pass those arguments, right? And it makes sense to put those arguments on a stack, right? Because that stack is there, right? So we will waste a little bit of a stack space if so, meaning that, which is kind of funny. So if you invoke this in x86, a program with a very long string, you can crash it, right? Because maybe it will run out of stack almost instantly. And what will happen when you pass an argument which is larger than a stack size? Well, exec will fail, right? But you can kind of fool a program into such position that, okay, there is really no stack space left because everything is taken by those arguments, right? Okay, this is like another example. So you're calling a myprog and passing through argument dog, cat, and frog, right? So argc will be 4, argument 0 will be name of the program, myprog itself, and then there will be dog, cat, and frog. And so those are strings, so they are not terminated, right? Let me ask you the following question. So what is this business of passing the name of a program into the program itself? Why is it useful at all? Who knows the answer?
You can implement different behavior based on how it's invoked, and some programs will do this like a busy box.
Yeah, I know, Shane. You're taking this class the second time, right?
Well, that one I just figured out at work.
Yeah. Oh, you figured it out at work? Okay, cool. No,
Yeah.
very good. I mean, I didn't know, to be honest, so I had to look it up the first time I ran into this problem. Okay, this is what Shane is saying. So remember environments like BusyBox. Environment like BusyBox don't have individual binaries for WC, grep, what else do you like, ls, anything, right? They say, okay, we'll implement everything with a single binary. Let's call it BS. And I don't really know what the name is in BusyBox. BS is kind of a bad name, right? Now you say, okay, question, how do I know which of these was invoked if everything is implemented by BS, right? Maybe it's WC, maybe it was invoked as grep, and maybe it was invoked as ls. And like to begin with, like what are those WC, grep, and ls? They're symbolic links in a file system. Essentially, it's an alias. WC will have a pointer in a file system to this busy, okay, let's call BS, BusyBox, right? And so by passing this argument, when the BusyBox will be invoked as WC, you will see WC here. And inside your code, you can check this first argument and check whether someone invokes you as WC or invokes you as grep, right? And then you can implement different logic. You can implement logic of WC, or you can implement the logic of grep. So is that clear to everyone? Shane, I believe, was in the undergraduate version of this class as well. Okay, good. But the fact that you figured it out at work is very impressive. So I never really like programmed BusyBox a lot. So I wasn't like connected to this community, but this is essentially the reason. And what's the historical reason? I assume this is it, but I don't really know for sure, right? That's the most useful use case today. Okay, so arguments to main are passed on the stack, right? So how can we implement it? So reasonably simple. We will copy all arguments. Essentially, those are strings arguments on the stack, right? So essentially, if this is the user stack, right, it starts, if we allocate it a page, right, but we go to the top of this page and say, okay, look, this is the very top of it. And we'll say like, copy the strings here. So, I mean, order doesn't really matter, but we can pick any. So imagine we say hello. Imagine we invoke something like, we invoke a full program with two arguments, hello and world, right? So we copy hello on the stack. We'll copy world on a stack as a string, right? Then we say, look, we have to make sure to create the arg vlist on a stack, right? So essentially on the stack, we will allocate argv array. We will update the pointers, right, to make sure that they point correctly to those strings, right? And then we will allocate argc, saying that this is 2 here, right? And at this point, this is the value of the ESP, and the user program will start running. Are we good on that, or something is missing? What do you think? Let me switch to chat. What is missing in this stack layout? Remember, return, exactly, Matt. Okay, I'm surprised. So remember, normally the call of, if we would really call foo or really call main function, which the program starts executing, like compiler itself doesn't treat main in any special way. It says, okay, this is a main function. So if there are some arguments passed to main, I will follow the calling convention. So they have to be on a stack, but they have to be above the return address because someone must have called main. In fact, you can call main multiple times in your program. It's okay, right? So it's a little crazy, but it's doable, right? So you have to put like 4 bytes here with some dummy return address, right? So it doesn't have to be anything. So usually you can put 0 just to make sure that you crash in some meaningful, clean way when you reach this, when you try to return from main, if any, right? So maybe 0 is not the best thing because 0 is actually mapped in x86 and it will continue running. So let's put some, like I would put some address which is above the second in a second gigabyte range. That this way we know for sure that this is unmapped, and we can cleanly terminate the program if it suddenly accidentally returns from main, right? Got the point? So essentially you will see it, right? So once in a while you will try to return from main if you're coding against x86 or coding a program for an x86 environment. You often forget to do exit instead of return, right? And then you return and crash, right? Okay, so let's quickly take a look at the code which does this. We got the high level story here. We allocate those arrays on this on the stack. So essentially what we do here is this code is a little hairy, so I'm not sure if it's worth spending time. Essentially what happens here is what is going on? So we are in a loop, right, for all arguments starting from 0 to the max argument, argc, right? We are essentially incrementing. We're taking the length of the argument which we're passing to exec, because those came from user level, right? Remember, we sanitize the input from user, right? But we're executing an exec system call, right? So essentially we say, look, this is the size of this argument plus 1, because there is 0. String len returns just the length of the string, right? So this is the stack pointer, and we're reserving the space on the stack. So sp, we say, look, imagine it's hello. It's 1, 2, 3, 4, 5 bytes plus 1, 6. So we essentially sidestep 6 bytes here, and sp is currently pointing here, right? What do we do next? We use this function, which essentially copies this string on the stack. So this will be filled with hello, right? Agree with this? And then we will keep going. We have a special data structure, which useStack, which records the position where this argument actually went, right? So it's in a reverse order, because we're going to push them in a reverse order, right? No, actually, doesn't matter. It's in some order. You get the order here, right? And at some point you say, look, we're gonna do that for each argument. So this is a fake return address. As I was saying, 0 doesn't work very well because you might return to 0, but the top of the address space, the very address -1, it's a good candidate. If you try returning there and running, the kernel will crash, right? So this is the user stack itself. We kind of form it here. Then we form the argc array. Then we form the pointer to the argv array, right? And essentially what we're doing here, we again reserves, like after we pushed all arguments to this stack, we reserve this spot for this argv for the 3 arguments, which for the 2 arguments which we're pushing on the stack plus the return value. And then we essentially copy this user stack to the actual stack location over here, right? So again, maybe I was going a little bit too fast, but I'm pretty sure that if you carefully watch the lecture again and read through the code, you can understand it. It's not super important. This is the minor detail. This is kind of its low-level programming of where the data, like where these arguments go on the stack. It still makes sense to understand it because the kernel is so small that you can read it all. But again, I'm not asking you to understand everything. I can ask the questions about it, and like I used to ask in the past, but I kind of mellowed a little bit at this point, but I may. Any questions about this layout? Did you get it? You probably got the high level picture, but not the low level details because I was going too fast. Any questions about what's going on? So useStack is actually like a local variable. So we create everything in this local variable first. This is useStack. Not everything. The strings we push immediately on the stack, right? Hello world will be here, but the pointers, essentially the return address, which is here, return, and the point, like this is argc will be like 2 in this example, right? This is 2, and then this one is a pointer of the argv array, right? So essentially, it's this location on the stack. We'll put it here. Excuse me. And then we will just in a single copy out function, we will copy this over to this stack, hence creating a correct stack, right? Because the return value will be at the very bottom of the stack, right? And we are updating the stack pointer to point to this location. Okay, good. No, actually, why mask minus, why, why not, where is -3 here? You mean this? Here, strlen -3. Good question. And okay, you deserve a point again. I didn't notice this. Who can tell me? I know. I think I know why, but maybe you know as well.
Why is that a minus?
It's not a, yeah, so what is this -3? It's not a minus, it's complement of 3. I'm asking except the last 2 bits, so why? So do you, wait, first of all, it's not -3, it's a complement of 3. Let me erase everything. So -3, it's not minus, it's complement of 3, right? Which means that 3 is 1, 1 and all zeros, right? And so on. And complement of 3 is 1, 1, 1 and everything but zeros, right? Agree with this? So what is the kernel doing here? Truncating. It's not truncating actually. Rounding down. Exactly. So it's alignment. I believe this is alignment. Because look, imagine the stack pointer lands like on a not aligned value. And you say, look, well, let me align in the 4-byte granularity. Why specifically 4-byte? I don't know. So why they decided to align in this, since x86, I mean, the compiler will align everything to what? To 16-byte granularity, right? Which to make sure that SIMD instructions will execute correctly. SIMD instructions are not used in x86 kernel, right? So I would say we don't have to align, right? But why would they align to a 4-byte granularity? I should admit I don't understand. There must be some reason. So maybe dig through the Git history to make sure that you understand. Maybe there will be a comment for why they align it, right? So good question though, appreciate it. I can dig it up for you as well and come back on Piazza, for example, to make sure that we all understand. But maybe one of you can dig it up and also explain it to the rest of the class, which would be fun. Any other questions? Let me actually quickly. So one possible reason is that copy out uses some like maybe it uses some assumption about alignment, but I don't know for real. So let's take it offline, just not to waste time, right? But we at least understand what's going on. Okay, we created the stack of the program, right? We created the arguments in that stack. We're ready to run. We created this address space. At this point, we can actually switch the page table, right? This is the function. So we're inside the exec function. So we're going to switch the page table. So this will actually switch the TR3 from the old page table, right, to the new page table. And at this point, we say exec will not fail, because if it will fail, that it means that there is no return at this point, right? So maybe the process will be just destroyed, but it just doesn't fail. And the next function which we will invoke is we will free the old address space, right? So I'm asking the question typically which page table we are deallocating, but I already told you it's the old address space of the process, right? Before exec. Remember when we were talking about the kernel interfaces and we were thinking of how exec is executing, right? What should happen for the exec to work, right? I was saying, okay, like it completely reloads the address space, whatever you have some main, maybe it was WC, maybe it was shell, and you reload it completely with WC. So this is exactly what we covered in these two last lectures, right? But effectively what happens is that this had a page table. This is an address space, and this had a page table as well, right? And so this is a CR3 register, and we're flipping from one to another. So, and now we have to deallocate this one. So how do you think we can deallocate an address space? What needs to happen?
We need to add those pages that were used to the free list.
Right, so we actually should walk the page table entry by entry, because we don't really know which physical pages are pointed by those entries, right? We have to walk the entire page table and pick up all non-empty entries and essentially like free them back to the memory allocator, right? So this is what essentially will be happening here. Let me again quickly look it up. So the process has two parts: user part of the address space and the kernel part of the address space. Probably doesn't really matter for the purposes of deallocation. It's just that you have to walk the page table, right? And then when you did walking, don't forget to deallocate the page table directory itself and deallocate pages that contains the page tables, right? Not only the page tables, the pages that belong to the process, but the pages which contain the page tables themselves, right? So, okay, so this is the function which does it. So there is this dealloc user part of the virtual address space, right? So okay, it actually there's this tiny nuance here, right? This is funny. It does treat the user part and the kernel part of the address space differently, right? So why? Who can tell me? What is so special about the user part and the kernel part? We have to actually treat them differently, right?
The user part is mapped twice. Is it?
Yeah, the user part is mapped twice. This page will be actually mapped twice. So of course it has to go to the pool of free pages only once, right? Right? So when we deallocate user virtual memory, we will add it to the pool of free page tables. But to deallocate the kernel part of the address space, we don't really have to free this page again. It's already freed and we want to avoid double free. So what we do instead is that we're simply saying we're going to walk through the page table, right? Because we already deallocated the user part of the address space. So all of this is deallocated, the first 512 entries, right? And the top entries, we're just going to walk through them. We're going to check if the page table entry is present. And instead of deallocating the page itself, we just simply deallocate the page table, right? This is what happens here. So essentially, you do this trick. If this one is present, right, it means that you get a page table entry and a physical address of it, right? From this, from here, right? Sorry, let me just use a different color. Change pen color again, blue. So we get this entry. It points to this page, right? So this is the entry, page directory I. This is it, right? From this, we take a physical address of this page, physical address. We again use P2E to make sure that, okay, this page, imagine this is page table. So this is the page table page. It's mapped somewhere over here, right? We use a P2V conversion, use a virtual address of that page, right? V, and we put it on a free list, right? So the page tables themselves, we do put on a free list, and this is the page table directory, right? This is the virtual address, we put it back. But those pages which are mapped by this page table, we don't have to deallocate. Is it clear? It's a little unusual, but again, like a tiny detail, but this is the level at which you have to understand the kernel code. It's kind of like multi-dimensional a little bit. It's not just like there was an array of objects, you have to deallocate them. You have to understand what consequences it might have. Did you get it? And for the dealloc UVM, the procedure is reasonably similar, right? So first of all, it's a page table, right? So you say for every entry, so you round it up for every entry A, you're going to walk the page table with this walk page table directory function. Remember, I told you once that the walk page table directory function will come up many times. It's a very useful function, right? We get this entry PTE, which is right exactly this, right? If it's not present, right? Sorry, if it's not, if it's 0, there is no PTE, you just go to the next address, right? So you just keep scanning. You're scanning you're scanning from the old size to the new size. Why is that? Why can't you scan from the beginning to the end? What do you think? Why don't you start from address 0 and go to the proc size? Why do they actually instead do from old size to new size? This is old size and this is a new size. Why do you think they're doing this? And they're deallocating page by page here. To be honest, they increment it. So new size, they go from new size. Yeah, they go from new size to the old size. Sorry, but who can guess why it's this way versus like going from 0 and to the proc size? The question you might be asking yourself is whether this function d_UVM might be useful in any other scenarios, not just when you kill the entire address space with exec, but for example, when someone executes an SBRK system call and actually frees the memory. It's the same scenario, right? So the proc size shrinks, so it goes from the old size to the new size, right? And you can reuse the very same function. You don't have to implement it twice. It's the very same code which can deallocate memory in this example, right? Because like imagine your program allocated a bunch of memory with malloc and then freed a bunch of memory. And at some point malloc says, okay, look, I will free this memory back to the kernel because I'm no longer using it. So it will invoke SBRK, shrinking its address space, right? And this function can be used happily in that scenario as well, right? Got this point? Okay, good. And the logic is similar. So if entry is not there, we just go to the next page. If the entry is present, right? So present bit is not 0, this one. Then we take from this PTE, which we have here, we take the physical address, right? If it's 0, then we panic, something is wrong. If not, we do the physical to virtual conversion, free the page, and essentially keep going forward, right? And here we actually deallocated the pages themselves, right? So I was actually wrong when I was said that these treats starts from a 2nd gigabyte. So it deallocates all the entries here as well, right? So it starts from entry 0 and goes to the entry 1024. It's not the most efficient code, right? To be honest, because it will touch on each of these entries, right? But it will treat the user part and the kernel part symmetrically. And at this point, it will just deallocate the page tables, the pages which contain the page tables, and eventually will deallocate the page table directory itself, right? So, okay, so we got the point. So this is how it works, I hope, right? Again, I might ask questions on the final about like, explain the logic of this function. What is it doing, right? And like you have to read the source code at this level of details and to be able to understand and answer those questions. I might ask tricky question as well, like implement a change in an x86 kernel, like what needs to be done to support this like special feature, for example, right? Okay, so we deallocated deallocate level 2. This is exactly what deallocate page table directory itself. Okay, so what did we learn? We learned how exec works, right? We start this on Monday. We started with the exec function, right? Right, and we understand how it works now. So it essentially creates the new address space, creates the kernel part of the address space first, then uses two functions, alloc UVM and load UVM to load those pages from disk, and that runs in a loop for each program header entry, right, from an L file. And then eventually you did that, you create a stack here in a guard page, right? This is a stack. You pass arguments on a stack and stuff like that, right? So far, so good. If I ask you a question, okay, you created it, but the process is not yet running, right? So, and in fact, the very first process is not even running, right? We assume that some process is already running and it invokes the exec. The question is, how is the first process in the very first process in the system is created, right? Let me quickly explain it, right? It's at the very end of the main function, not at the very end, but here, user init. It creates a new first process. If I ask you a question, how would you create a first process in this system? What would be your outline?
It would be similar to exec.
It would be what?
Similar to what we have done with exec.
It would be similar to exec. That's not a bad idea, but maybe you can do it simpler. Because if we already have an implementation of exec, why can't we use a tiny small assembly sequence, which we have to start it at user level, and it will just do int 64 by providing the number of the exact system call in EAX register, right? Then this will follow the like if we pass arguments to the exec, it will implement exec and replace the address space of this very first process with whatever you want to run there, right? It's much simpler than just doing everything again, right? So, and this is what xv6 is doing, right? So first of all, it allocates a new process, right? So this function allocproc is the one which allocates the process data structure. And the process data structure in xv6 is actually this. Again, fits on one screen. Remember, I told you that once, if anyone during the job interview will ask you, what is a process? You can either try to remember from a book, which you read maybe earlier on, right? What is the process, and like start blobbling something. But really, if you open this, if you have a chance to look at this data structure and explain every field, you will explain what the process is, right? Important fields here are the page table directory, right? The address space of the process, the kernel stack. You remember the interrupts when you transition from user level to kernel, right? The interrupt has to execute on a new stack. So make sure you explain this to the person who interviews you. You will get some points for that. Enum, which tracks the process state, whether it's running or it's like waiting on the IO. Process ID, we'll see why we need it. So pointer to the parent process, again, to notify with a wait system call why the parent is there. The struct drop frame, so essentially that's the pointer to the registers, to the user registers, which is saved on the kernel stack, so the kernel can update them or like provide an like a return value from a system call, right? Context, it's part which involved in a context switch. We'll cover it next time. This field is involved in slipping, and when we get to synchronization, we will understand what this field is. Its field is whether the process is killed or not. File descriptor table, open files, right? Remember, each process has an open file. A pointer to an inode, which represents the current process directory, right? So when you type dot, this is what this is where the directory is, right? And the name of the process for debugging purposes, and the size of the address space, right? So again, I kind of rapidly explained those fields, but as we move a little bit forward in this class, I'm pretty sure that by the end, you will be able to confidently explain the meaning of each of these fields, right? And essentially, this is how you can explain what the process is. Okay, so what do we need to do to create this user process? We allocated this data structure. Obviously, I told you important field is a page table. So we have to create a page table, right? We first map only the kernel part of the address space, right? And we do have this with setup kernel virtual memory function, which maps this with a 2 GB shift all available memory, right, up until fizstop, right? We get a page table back, and now we use this function, which is init-uvm. It takes this tiny assembly sequence, which we linked into the kernel, right? And we use a specific linker magic. So we have these two symbols, which we use with an extern. Those symbols are created by the linker. You can take a look at the linker script, which we use, which x86 is using to understand how those symbols are introduced, right? But essentially, it's a tiny assembly sequence, which essentially just invokes the exact system call, right? This is what I was just talking about just 2 minutes ago, right? Okay, so init UVM, instead of like doing load UVM, like reading an elf, you could have done it, but it's a little bit more complicated. But just like it allocates the pages and loads them into memory, right? Here I was again emphasizing the fact that each process has a kernel part of the address space mapped into it, right? So just to everyone probably already remembers it, right? So init UVM so says I actually will only allocate one page because I believe that the size of this, right? So we check if the size is larger than a page, the size of this assembly sequence, which we passed here, is larger than a page, then just exit, like something wrong is going on. We're not going to initialize the init process, the very first process in this manner, right? But then you set this page with zeros, right? And then you map pages, right? Because again, we remember how to do that. We say, look, it's the same map pages function. Now we again map a single page at address 0, right? And what is this page? We just allocated it. So we use this v2p macro to just say that this is the physical address which we're mapping. And then we're simply moving this init sequence into this new memory. Since we know the virtual address, here we don't really have to do any P2V conversion. We already have the virtual address of this page. Just quickly, because we just allocated it. In previous example, alloc UVM allocates pages, and then load UVM loads them. That's why we had to walk the page table. But here we just allocated the page, we immediately load it, right? You can write it this way as well, right? What is this init sequence, right? The init sequence is this. So it's a string of assembly. It just invokes the syscall, and specifically the sysexec syscall, right? So it pushes 3 arguments, right? It actually pushes 2 arguments, and this is probably, who can tell me what it is? I probably know what it is, but can you tell me? Remember, normally a syscall would be invoked like push an argument init, address of init, then call a function exec, right? And this would put a return address on the stack, right? So instead of like, we reserve the space on the stack, so the kernel is not confused because it doesn't know that you invoke it in this from this specific context, right? So it will actually reserve some space on the stack, right? And then you do a syscall, right? And those strings which you have here, the init string is the name of the init process, and the argv is constructed in assembly as a pointer to the init. And why do you have to put 0 here? Argv has to end with 0 according to some convention. I didn't know that, to be honest. I didn't know that you have to pass. No, but null termination of string is this. This seems like a null termination of the argv array. I don't really know why do you need to null terminate of argv, because you are pushing okay, I have a call from a spammer. Sorry, let me think. Let me just like hold on. So what's going on here? Who can tell me quickly? I'm lost a little bit. So this exec takes two arguments, right? So one is, what are the arguments to exec? The name of the process itself, this is init, right? This is where we name I will be looking the inode in the file system. And the argv is an array. Okay, got it. No, I didn't get it. So, okay, I got it. Okay, sorry. Yeah. Sorry. Now I got it. So I got confused. The main itself, the main takes argc and argv, and in exec, argv is null terminated. Got it. I get it. Sorry. Thank you for correcting. Yeah, I apologize for that. So essentially, exec just takes two arguments, right? So that goodness, I wanted to quickly switch here. So where's our wonderful bin source code of x86 kernel? Let's just let me show it again. Edit user h. So if you have an exec here, right, it just has two arguments. So it's the name of a program itself and argv by, since we're not passing a size, so argv is null terminated, right? Okay, we get this. Thank you. Okay, so, and this essentially lands us on the into the kernel, right? With this exec call, right? However, it's fine. We created the address space. We may even put it on a scheduler queue, but in order to run, and it's a little bit tricky here, you need to make sure that you pretend that the kernel stack of the process has this trap frame here. Why do you think it is? Why do we need it? And it's not entirely clear right now. It's kind of like a chicken and egg program, right? But remember that every time we context switch from a process, imagine this process, we kind of need to pretend that this very first process was already running in the past. Because for the kernel, the only legit situation when the process is parked in a kernel is that it was preempted with an interrupt, meaning that it already had a user stack, and then imagine like some interrupt in the past. Maybe it was a timer interrupt, maybe it was an interrupt from a device, maybe it was even an exception, like division by zero, but then the process would be killed, right? Preempted the process and created the trap frame data structure on the kernel stack. Then this process can be placed on the scheduler queue, and the scheduler will pick it up at some point and will switch it to it, and will exit like essentially will follow the standard exit from the interrupt procedure, where like you will remember unroll the trap frame, will stay like will leave only 5 arguments on the stack, and then use an iret instruction which will restore the context of the user process, right? So this is exactly what x86 is doing. It pretends that this process was preempted by the interrupt, and it specifically creates a specific stack on the specific entry on the kernel stack of the process. So this process can be exited back into the user level, right? Okay, so let's take a look at how it should look. Again, it's the same what we like looked already, like the first 5 fields which are pushed by the hardware, then an error code, and the number of the interrupt, which is like pushed by the vector 32, then all the general registers, right? Everything, right? So, and this trap frame is part of the process data structure. Remember, every time we enter into the kernel, we update the proc trap frame with the trap frame value which the trap function receives as an argument, right? Remember this? Okay, so this is what we're doing here. So we will allocate the kernel stack because each process will need a kernel stack. So it kind of like can be preempted with an interrupt, right? So we will initialize the process state as unused for now. So the scheduler don't yet try to execute us because it might, and we're not yet ready. We initialize the kernel stack to be at this SP, so essentially the kernel stack page plus the kernel stack size, right? So at the very end of the page, we leave a little bit of room for the trap frame, right? Essentially, and this is how we initialize the trap frame data structure. So this is the kernel stack, SP now points here, and this is enough room for the trap frame, right? And the proc drop frame points exactly here, right? At this point, we just have to create this drop frame and the kernel will follow. So we say, okay, hold on. We know how to create the drop frame. We initialize it with zeros. All the registers are zeros, but we want to exit into the user level. So we'll initialize the code and data segments to point to the GDT entries, which essentially point to the privilege level user, right? Essentially, we want to exit into the user, right, from the kernel, right? We initialize all the ES and SS registers from the data segment itself, so they all will have user privileges, right? E flags, we initialize the interrupt flag as disabled. Why is that actually? No, we actually initialize interrupts as enabled. I'm wrong. Why is that? Is that to make sure that when you exit into the user level, the interrupts will actually be re-enabled, right? Otherwise, you will exit into user, and it will never get an interrupt back. It's a very good, again, homework exercise to say, let's change this line and see what will happen, how the kernel will behave. Great, like, again, great question on the exam, right? So the user stack, essentially, we say, wow, remember, we mapped only one page with this init sequence. We're setting the user stack at the very top of this page. We barely will use any stack because there were like 3 instructions and we don't push anything, but so whatever, let's do it. And instruction pointer is address 0, the beginning of this init code S. This is the init sequence which we just looked at, right? So, and that seems to be correct. So all the registers are initialized correctly, right, on the drop frame. When the kernel will exit from this drop frame, it will start running the user code exactly here, right? Instruction by instruction, this sequence, right? Okay, cool. So we will initialize the name of the process with the init code. We will set the current process directory to name I of the root folder, right? So it's an inode of the root folder. That makes sense. And now we are ready to set this process to runnable, right? Meaning that at this point, if scheduler will pick it up, we're good to go, right? At this point, again, let me stop since I'm already 3 minutes over. We're almost there, so it will take us just a tiny inch of a second to understand what the kernel is doing. But to be honest, it will become a little bit more clear when we get through the next lecture, which is a context switch, and then we'll be very clear on how the kernel switches between processes, and then we'll understand how the scheduler will pick up this process and essentially exit into the user level. But again, so hold on until the next time. Again, thank you for your time. If there are any questions right now, go ahead, ask them. If no, run for your next class. Okay, thank you guys as well for joining me. So see you, some of you.
Professor.
Yeah, go ahead.
I have a question about Redleaf, if you have a second.
Yeah, absolutely.
I don't have that much time, but is it possible to run without TPM support? I was just trying to compile and run it, and it looks like it doesn't work on WSL due to timing out trying to communicate with the TPM.
Right. No, first of all, like compiling Redleaf and running it is an adventure on its own. So
it booted. It got pretty far into the boot process.
Yeah, good. No, then just disable the TPM. So essentially, TPM we use only in one sub project, and we don't need it anywhere else. So yeah, it does run without TPM. In almost all scenarios, it doesn't need it. So just try to disabling it. It should boot.
Okay. Should I only need to change the make file, or will I need to like stub out some functions? Do you think?
I mean, I wasn't the one who was committing the TPM code. I think it was Vikram. So I think there will be just some kind of a feature flag in one of those cargo files to control the TPM.
Oh, in one of the cargo files.
Yeah.
Okay, cool.
Yeah, I think, and also we switched to a new build system. I don't know which version you're compiling, so most likely
whatever's on the master branch.
Yeah. Most likely, yeah. I don't think we use a lot of make files these days, so mostly we use cargo for building.
Oh, so is there do you just do all, is the newest version on the master branch?
I think so. Yeah, should be at least something usable should be on the master.
Okay, I mean, it still has some make files, right?
Yeah,
Like,
yeah, it does has some. It does.
but like
have
the
some.
underlying builds are gonna
Yeah,
be,
yeah, absolutely.
okay. Okay,
Yeah.
cool. Yeah, I was just trying it out because
Yeah, if you
it's
run into
neat.
if you run into real problems, I would say just shoot us an email and we'll add you on a Slack channel, which will like where people will help you with Redleaf.
I think I'm in that Slack channel actually.
Oh, then ask there on the Redleaf channel on the Redleaf. If you're already there, go for it.
Okay, thank you. That's it.
Yeah, you're welcome. See you guys.